Okay, good morning. Let's continue on a triple integral here. Okay. Just a quick review in terms of how to evaluate triple integral using Cartesian coordinates. This is basically the appearance of the triple integral we typically deal with. And this is a general formula. This one actually doesn't tell you whether you're evaluating using triple integral using Cartesian coordinates or using any other coordinates, which we'll cover today. Okay. So if you're choosing Cartesian coordinates, basically the dv over here can be written as the three coordinates, basically the domain variables dz, dy, dx. Okay. Your first step, okay, is what we so-called the order. Okay. So decide on the order of the integration. For Cartesian coordinates, there are 6 combinations. It doesn't matter, a lot of time doesn't matter what the order is, but dz, dy, dx could be I'll show you a different order, could be the typical order that you choose, okay, dz, dy, dx. If this is the order we choose, then the second step, basically whatever order that you have chosen, then you draw a shadow, okay, in the xy plane, basically in the plane for the last 2 variables. Okay. So that's why the order is important. So draw the shadow in xy plane. Xy plane is the last 2 variables in the order of integration. Then step number 3 is to decide on the limits, integral limits. As we learned in the previous lecture, how you design the limits is pick a point inside the shadow and then draw an arrow line in the positive z-axis direction. Your first contact give you the z mean. Second contact give you z max. And the next step is you draw an arrow line, okay, in the y positive x-axis direction, because the second order is y. The first contact give you y mean, the second contact give you the y max. Okay. So that's the 2 limits for y. And last step is you sweep this second arrow line across the shadow. Find the limits basically for x mean and x max. So the last limits for x must be constants instead of variables or functions. Okay. So basically your x mean could be a constant a and max could be a constant of b. So those are steps to basically go through this scanning process to find the limits. I keep emphasizing on the scanning concept. Now if you look at the steps finding the limits, the same idea applies to all different kind of coordinate system basically. Okay. If you look at the first step, you're scanning you're going in the positive z-axis direction, so you're scanning in that z-axis direction, and that's what you get, right? For this first step, after scan, you go through here basically. The second step, you're scanning in the positive y-axis direction, right? And last step, you're scanning in the positive x-axis direction. So if you have just a single variable function, a to b, f of x dx, this is also scanning. You're scanning from a to b in the positive x-axis direction. Right? It's as simple as that. The multiple integral, it just involves scanning in other, doesn't matter which one, how many integral you have, a double integral, triple integral, involving 2 or 3. So you just have to go through the scanning process, right, in the axis direction. Okay. Yeah. Okay. Let's take a look at a couple of examples that are here. Okay. I'll draw you a region in here. Okay, so basically I'll present the region. So region D is given. Here's what region D looks like. It basically it's the corner of a certain walls. Okay, 3 walls corner, and then on top of that you have a plane in here. So this plane right here is x plus y plus z equal to 1. And region D is whatever below that plane and also on top of the other 3 sides of the walls here. Okay. So we wanted to calculate, we call this is a tetrahedron. What is the volume of this tetrahedron and here, or basically what's the volume of this region D? The formula wise, I think we learned in the previous lecture, when you calculate volume, basically the function that you're integrating is 1. Okay. If you let the function f of x, y you're integrating equal to 1, then this triple integral will give us the volume. So if you are in high school, without even learning triple integral, you probably have a formula to calculate this kind of volume at tetrahedron, right? So that's doable. But let's use triple integral to evaluate this volume at here. Let's follow the steps. Okay. Step number 1 is you're gonna. What's my step number 1? Step number 1 is determine the order. Okay. So let's use the traditional order here. dz, dy, and dx. Let's choose this order. And the second step is once you decided on the order, and then you need to sketch the shadow of this object or the region D. You sketch the shadow in this case in terms of the last 2 variables. So in the xy plane in this case. Shadow basically means you project into the plane, vertically. So in this case, my shadow will definitely be the bottom triangle at here. Okay. So once we decided these 2 steps, then the second step, shadow in xy plane. This step. The next step is determining the integral limits now. Let's follow the basic integral limits. We will put in the limits for the 3 integral at here. Right, we're integrating with respect to 1, so nothing needs to be here. Okay. So let's follow the steps. First, pick a point inside the shadow. Pick a point somewhere inside the shadow here. And then we draw a vertical line in the positive z-axis direction. Basically scan in the z-axis direction. Okay, so that's the line we draw it here. Follow the line, find the first contact point and the second contact point, and then find expression for the z-mean and the z-max. Z-mean is pretty simple. It's bottom of xy plane. Basically z-mean is 0. And z-max falls onto this plane. And this plane is given already. So z-max must be what? What will be the z-max? Y minus x minus y. Okay, good. Okay, that's simple. That's for the z-mean and the z-max. Next step is to find the y limits. You deal the y limits using the shadow that you have just sketched. The shadow is over here, it's a triangle, so you draw the arrow lines in the positive y-axis direction. Follow the arrow line, find the first contact and the second contact. First contact falls on the x-axis, so your y-mean must be 0. Second contact falls onto this edge at here. So this one needs a little bit thinking, okay, in terms of what's this edge here, right? The question didn't directly give you an expression for this edge. So we have to derive something based on the given information. This edge is the intersection between the plane x plus y plus z equal to 1 and xy plane. So then what will be this line equation? So basically 2 planes intersecting give you a line, right? We need the line equation at here. Then what will be this line equation then? That's right. So this intersection xy plane means z equal to 0, right? For xy plane. You substitute z equals 0 over here, you get x plus y equal to 1. Okay. So that's sometimes the question doesn't give you all the information. You have to use a little bit information derivations here to derive the necessary condition. Okay. So now I have my y max, which basically is y minus x. Good. Last step, determining the x limit. X limit is to sweep these arrow lines in the positive x-axis direction. Find the edge, the 2 edges, sandwiching this shadow. Apparently the first one is 0. The second one is a line passing through this vertex at here. So again, you have to decide then what's the coordinates of the vertex there, right, of the point. It's actually pretty straightforward. For this particular point, I mean, this is x plus y equal to 1, and this line here must be what? This is in the xz plane. This must be x plus z equal to 1. Okay? And this point at here happen to be 1, 0, 0. Okay. So your x max is 1. Okay. So once you have this done, the rest of the work is just integrate one by one from inside to outside. Okay. And when you're doing the integration with respect to the z, always remember you're treating x and y as constants. Likewise for the y, and then at the end to do with the x. Right. Okay, so I want you to practice these integrals at here. Okay, you should get a 1 over 6. Okay, as a result. So if you use a high school formula, what's the formula for the tetrahedron? 1/3 times, yeah, times the area and then the height, right? Yeah. So you get it 1/6. Okay. Okay. That's a simple example. Let's take a look at another one, the one that we keep crashing my computer from previous lecture. Oh, that's ominous. Okay, so here's a different region at here. Okay. This region D has 4 sides. So here's the region D. Pretty much another tetrahedron. It has 4 sides. This time, this plane and here is y equal to x plus z. And the other side is y equal to 1. And plus the bottom side, which is the xy plane. And another side is the yz plane. So these 4 sides give us this region D and here. So let's try again to calculate this volume for this tetrahedron. Okay, it's not about the integral technique, it's about finding the limits here. Okay, so the key here is you need to be able to find the limits appropriately by following the procedures. So let's do this, but this time I will try a different order. Okay, let's take a look at really, does it really matter or not? I'm going to try dy, dz, and dx. So different order at here. If this is my order, then the second step, if you recall that, then we need to sketch the shadow. Sketch the shadow in the last 2 variable plane. So basically in the xz plane. Project this whole thing, okay, into xz plane, and then that gives you the shadow, right? So basically project everything into your xz plane. So your 171 is working at here. That essentially give you this triangle at here. Okay? Yeah. So there are some missing information we need to figure out, not just doing the projection at here. Okay? Yeah. For example, what will be this line equation over here? What will be this equation for the edge? Okay, so we need that information. So this edge comes from where? From the projection of this edge. Okay? Yeah. Essentially, you have, if you look at this portion here, right? If you expand everything, you basically you got a plane intersection between this plane and this xy plane at here. Okay. Yeah. So let's take a look at the given condition. If this is a plane y equal to x plus z, and this is what plane? This is a plane of what? Y equal to 1, right? So here's 1. So basically you have vertical plane at here. Then these 2 planes intersect, give you a line. Okay, give you a line here. How do you get that intersection line? You substitute y equal to 1 into this plane at here. So you got x plus z equal to 1. And this line project to the xz plane. So you got x plus z equal to 1 here. Is that clear? So intersect between y equal to x plus z and y equal to 1 to give us this x plus z equal to 1. Simple substitution. Pretty much this is the key at here. Okay? Yeah. Okay. So let's follow this. The next step now is to find the limits. Once we have the shadow, then you pick a point inside the shadow. Then you draw in this order. It's y first, so we draw an arrow line okay, in the positive y-axis direction. First contact falls onto the plane. Second contact falls onto this y equal to 1 plane and here. So I'm going to put down all my missing pieces puzzle at here. So apparently your y mean, since it falls onto this plane, your y mean must be this x plus z. That's the plane, right, in general. So y mean is x plus z. Okay, so that's your y mean. So some of this are pretty straightforward, but some of this you need an expression. The next one falls onto this vertical plane here. It really doesn't matter which point it falls onto, it's always y equal to 1. So that gives you 1 over here. Okay. Second step, then you work with shadow now, right? Work with the shadow. It deals with the z first. So we draw an arrow line in the positive z-axis direction. First contact falls onto the x-axis, basically z equal to 0. Second contact falls onto the edge of the shadow. That's the equation x plus z equal to 1. So z equal to 1 minus x as the z mean. Last step, sweep this arrow line from one end to the other side in the positive x-axis direction. X means 0, x max is the coordinates given at this here, which is 1. So that gives you this limits for all three variables. And if you calculate this one in here, what do you think the volume would be? 1/6, same thing, right? Okay, so that's the procedure for Cartesian coordinates, finding the limits. Okay. It's not about integral technique right here. Okay, the focus is on finding the limits. Any questions on? Yes.
So we always find the shadow, and then our limit is regarding the shadow instead of object itself.
The shadow gives you the limits for the last two variables. The first variable is decided based on the actual 3D object, but the shadow, of course, is also given by the region D, right? So it's directly related to the region D. Yeah. Where? X plus Z? Oh, 1 you mean? So okay, that's a good point. The x max is basically the projection of this vertex onto here, right? Yeah. Or it's the intersection between this line and the x-axis.
What if we make an arrow to direction of x and say that the x min is 0 and x max was
the last step is sweeping, so we're sweeping this arrow line in the x-axis direction, right? Sweeping in the x-axis direction. So this is the two edges after sweeping. Yeah. Yes?
Why is our function just 1?
Why is the function just 1? Which function?
Like the function that you're integrating after x, y, z.
Oh.
You didn't know the 1 before you said it was just 1.
I see. Yeah, because we're looking for, in that question we're looking for the volume of this region D, right? To find the volume, as you can see, if I set this function to be 1, basically this is a triple integral general formula, right? So you're integrating this function over the region D. If I set this function to be 1, okay, so basically if you let f equal to 1, then you have an integral dv. And as I pointed out in the previous lecture, when you integrate anything, what do you get back? You get back that anything. In this case, you're integrating volume, so you get back this volume here. Okay. Yes?
So that fx, y, z, that's kind of like density then?
You can think of it as a density. But mathematically, it can be anything. It can be just a simple function. But physically, it can be a density. Or maybe some other physical quantity. Yeah. Yes?
I'm a little confused. Can you give an example of like what that would represent? If f of x, y, z is equal to something that's not 1, like if it was some function and then dv, what would that be?
Well, look, I appreciate you're thinking always in a very concrete example. That's as engineers, I think that's what we should do, right? But however, here I always also encourage, this is a pure math formula sometimes. Pure math, if you ask a mathematician, I don't know what density is, but I can teach you this pure math here, right? So what this is, hard to say. You have to associate that with the application. If you associate this formula with your application of calculating, let's say, the total mass of an object, then what this is? This is a density, right? If you associate this formula with some other different applications, maybe this is temperature. So maybe this represents the temperature at every point within the region D. Then you're integrating all the temperature together, right, within this region D. So it's really hard to see. So what is this f of here? In a very simple language, I would say f is nothing but just a function. But in the real application, then f has definitely certain specific meaning there. Does that answer your question? Yeah. Okay.
If f of x, y, z is a density function, it would be in mass per unit length, right?
Right. Density is a mass per unit, per mass over the volume, basically. Yeah.
But then, last minute.
Yeah. Density times volume give you a small mass, isn't it, right? Then you integrate all the small mass together, you get the total mass. That's actually how we derive this triple integral here. Is that okay? Yeah? Good. Yeah. Very good. I like the active thinking. A lot of students actually, when they come to my office, and they try to really think beyond what the lecture is covering it here. That's absolutely beneficial to your understanding of the concepts. Okay. Yeah. Okay. So let's continue at it here to consider another perspective. Basically, let's evaluate the triple integral using a different coordinate system. And this time we're going to use a so-called cylindrical coordinate system. So in triple integral, we actually have we'll cover three different coordinate systems. One is the Cartesian we already covered. The second one is what we're going to cover here now, is the cylindrical. And then next we'll cover this so-called spherical coordinates. Okay? Yeah. So what is a cylindrical coordinates? If I give you a point in the xy plane, so then you can describe this point using coordinates x, y, z. But this time, I'm going to describe it using another set of coordinates, okay, or variables. And this time, we're going to use this set of coordinates here. The first one is, okay, we drop that point, okay, into the xy plane, and we know that the height of this is z. Okay, so that's fine. Okay. And second of all, we can, once we find this projected point in the xy plane, we connect this origin, okay, with this point. And when you connect the origin with this point, as you actually learned, in xy plane, this is basically part of this so-called polar coordinates, right? Yeah. And there's also theta associated, okay, with that reading lines over there. So now together you have r theta z. So these three is another set of variables that can uniquely describe the location of these points. So unique, that's the important part, okay? Not anything like lacking information or redundant information. Using the three, you can uniquely describe the points. So essentially your r theta z, okay, for that point P will give you the same information as x, y, z, describe the same location. And this r theta z is what we call the cylindrical coordinates. Okay. So if x, y, z has x-axis, y-axis, and z-axis, then for cylindrical coordinates, very similarly, you also have three axes. So you have basically one axis going up at here. That's like your z-axis. Okay, so in the z-axis direction, because you have a z component at here. And you also have one axis going in the direction of this r, the reading line direction. So basically you have one goes this way at here, okay, in the r direction, goes out of this reading direction. This one here, we call that the r-axis for the cylindrical coordinates. And the last one, you have another axis which is in the theta rotational direction. So that has to be always perpendicular to the rotational of this line here. So that's your e theta r at here. Okay. So that's a coordinate. Basically, it's another coordinate system, r theta z, right? And satisfying this right-hand rule. Okay. So when you cross r to theta, you get a z. Okay. When you cross anything else, and then you got the other one here. Okay. I draw this one here because when we try to look for the limits, and we have to stick to the concept, we're going to scanning in that positive axis direction. But this time we're going to scan in the positive cylindrical coordinate axis direction. Okay, so let's look at first. Let's look at the connection between the Cartesian coordinates and the cylindrical coordinates at here. What will be the connection? First, let's look at the connection between x and the cylindrical coordinates. Okay. This is actually pretty straightforward because if you break it down to small pieces, cylindrical coordinates basically is the polar coordinate plus the z, right? So x at here essentially is r equal to x equal to r times cosine theta, just like the polar, and y equal to r times sine theta. And z, there's no change, still the z at here. Good? Yeah. Okay. Now I have my the connection now, and then the next question is how can we evaluate a certain triple integral in cylindrical coordinates? But before we do the evaluation at here, okay, and I want to ask you maybe to visualize. If I give you, let's say, theta equal to 45 degrees, just saying, here I have a theta equal to 45 degrees. What would you visualize in terms of this cylindrical coordinate? What type of objects will give it to you? That's right. Yeah, right. That's what I want you to visualize. Because if I tell you x equal to 1, you're not just visualizing x equal to 1. You're visualizing the 3D as a plane, right? Yeah. And similarly, in cylindrical coordinates, if you have a theta equal to 45 degrees, then you should also So theta equal to 45 degree refer to a line that's 45 degree, but in reality, you're extending it, right, up and down to get the plane here. Good? Yeah. How about this? If I say r equal to 4, what do you think that represents? Cylinder, right? R equal to 4 in plane, xy plane, it's a circle. But we're always talking about 3D. And so up and down to give you a cylinder. Okay. Yeah. It's not everything a cylinder. It's the surface of the cylinder. Okay. Yeah. Good. Okay. So let's focus on the evaluating this triple integral here. Bear in mind, we're not going to deal with x, y, z anymore, so we're going to transform this into r theta z. Okay. So how do we transform this into r theta z? First of all, if I'm not going to deal with x, y, z, then I'm going to replace this x, y, z with the corresponding expression that we find between the Cartesian and the cylindrical coordinates. So your x needs to be replaced with r cosine theta, y needs to be replaced with r sine, and z still keep it as z. So your function f, which is the function you're integrating about, has to do some substitution first. Okay? Substitute your original x and y with this, but you keep the z. dv, we are not going to deal with dx, dy, dx, dy, dz. Okay? So we're going to deal with dr, d theta, and dz. Right, that's what we're going to deal with. However, if you recall this kind of question at here, you are essentially choosing 3 completely different variables instead of x, y, z, right? So as we learn in double integral, instead of using x, y, if I use a u and a v, what do I do at here? Jacobian, right? Okay. So you need to find this question mark using a Jacobian at here. It's actually pretty straightforward. So your Jacobian, first step when you find a Jacobian, basically you have to write down what's the connection, right, between your original x, y, z and the new r theta z. So we create this, basically the so-called transformation vector function. You have your x function at here, r theta z. It's pretty straightforward. R is here, it's r cosine theta, right? So that's given already. Then you also have your y function. It's also given now. You also have the z. It's just a z. Okay. I'll write the steps at here, but in the future you'll just use the results. Okay. So here's your t at here. Here's your basically transformation function at here. Then the Jacobian is partial x over partial r, partial x over partial theta, partial x over partial z, right? Creating this Jacobian at here. Oh gosh. Don't do that to me. create create this 3×3 Jacobian matrix. It's very simple partial derivatives because you have this x, y, and z at here. So let's take a look at each one of the partial derivative. Partial x over partial r. So you look at this function here, and that's just give you cosine theta. Partial x over partial theta give you a negative r sine theta. X is not a function of z, so this partial derivative give you a 0. And then here give you sine theta, cosine theta, r cosine theta, and 0 here. Last row, z is not a function of r and theta, so both 0, 0 here, and z is just a function of z, and then partial z or partial z is 1. Okay. So you get this transformation matrix, a Jacobian matrix. Okay. Actually, it's a transformation matrix, by the way, here. Okay, yeah, so now you calculate the determinant of this Jacobian. Okay, once you calculate it's 3×3, but even though it's a 3×3, but there's also 2 zeros here. It's a much more simplified determinant calculation. You end up with just r. Okay. R is the part of the cylindrical coordinates, right? R here. By definition, the r is basically going to be greater than 0 because r is always the distance from a certain point to origin. So your r is by default is greater than 0. Okay. There's still a lot of time. Don't know what happened there. Okay, now we replace this question mark here, basically with r. So you're evaluating triple integral, okay, in cylindrical coordinates. So this is basically the new formula now. Okay. That's what happens. Good? Yeah. So what about the order, right? What about the order of integration? You still have 3 variables that are here. Literally you have 6 combinations. You can choose any combination to evaluate this triple integral. Typically, I'll show you a couple examples, essentially how to develop. But in terms of cylindrical, okay, you are given an object, basically up and downs with the bottom in the xy plane or something like that. So the order usually we choose dz, dr, and d theta. Okay, is the normal order. Okay, so typically that's the order we're going to choose. If you choose the other order, absolutely they're going to work. And actually, I'm going to show you how to choose the other order. Okay. Yeah, but I will demonstrate an example using this dz, dr, d theta, and then how do we find the limits for each one of the coordinates here. Okay. So let's look at an example. I'll give you a region D, okay, which is bounded by the following 2 surfaces. Okay. So here we have 2 surfaces bounding this region D, and I want you to be able to sketch these kind of things. I think you need to be very familiar now once you practice, because we have written this kind of surface quite a lot, especially the first one, z equal to x squared plus y squared. Okay. And this is a paraboloid, right? We have sketched many times. So you can sketch this paraboloid out. That's your one of the surface. Okay. And the other surface is 4 minus x squared minus y squared. So if I don't have the 4 in here, let's say if I just have a z equal to negative x squared minus y squared, and this is literally what? Just the opposite, right? The mirror of this paraboloid. And now you have another 4. What does that mean? Basically, you shift this whole thing and upwards by 4 units in the z-axis direction. Okay. So overall, you get another surface, another paraboloid essentially, but this time it points downwards. Okay. So that's another paraboloid, okay, going down in here. It's like you have 2 bows, one pointing up, one pointing down, right? And they're on top of each other. The middle space is the region D, right? So apparently these 2 paraboloids will give you somewhere in an intersection over here. Okay? Yeah. But this whole part is the region D. Okay? Yeah. Okay. So then let's think about an easy one in here. What will be the triple integral? Let's say x squared plus y squared and then dv. Okay, like that. Here's a step you need to follow, huh? Yeah. Step 1, decide on the order of integration. Here's what I'm going to do. So order, as I just said, I'm going to decide dz, dr, d theta with my order. Step number 2. Okay. Step number 2, very much like the Cartesian coordinates, is that you decide to sketch this shadow of this 3D in the r theta plane. Okay, so shadow in r theta plane. Well, r theta plane out here, it's basically what plane? It's basically this xy plane out here. Right? If you look at the r theta, okay, so this is r theta, so essentially it's the xy plane here. That's how you can find r theta limits. So maybe more straightforward is just think of it as xy plane, right, to find r theta. So if I look at my current object 3D, this region D at here, okay, this is the reason why I'm drawing this edge here. If I project this region D into this xy plane, so basically here's the edge, here's another edge. Once you project into it, you get this shadow at here. And this shadow, as we're going to see, is actually a circle. Okay, yeah, it's a circle centered around the origin. But for now, just sketch the shadow first. Okay. Yeah. Okay. So let's look at let's look at the shadow here. Okay, that's important because we need we need this shadow at here. Okay. So this is the shadow. So how do I find the expression for the shadow then? Right. As I said, the shadow is basically this intersection, and this intersection is between this paraboloid and the other paraboloid. So all we need to do is to find intersection, right? Using the two equations. And these two equations, what is intersection? Intersection basically means at that location, right? If you look at this, all of the z components is the same, right? That's what intersection basically means. So to find the shadow, all you need to do is you let these two equations equal to each other. So you have x squared plus y squared equal to 4 minus x squared minus y squared. And then do a little bit of simplification. Move the x squared y squared to the other side. So you got a 2x squared plus 2y squared. And divided by 2 on both sides, you get x squared plus y squared equal to 2. So this shadow here, basically it's a circle. What's the radius of the circle? 2? Root 2, right? Because I know a lot of students sometimes they write 2. Yeah. Okay, good. So time to find limits now. Once we have this step done, and step number 3, finding limits. Finding limits is about scanning in the direction of that axis direction. Okay, so scanning in the directions of axis. This time it's not x, y, z axis, right? It's the r theta z or z r theta. Now that's the other three axes here. Since I'm going z first, so what we do is we pick a point inside the shadow, okay, and then you draw an arrow line in the positive z-axis direction. That's how we scan. We're scanning in the z-axis direction first. Find the first contact point and the second contact points. First contact point and the second contact points. First contact point is the paraboloid, which is this paraboloid here, right? Second contact point is the top paraboloid, and the inverted one. That gives you the z mean and the z max. So let's write it down here. So z mean is x squared plus y squared, and the z max is 4 minus x squared minus y squared. But you might be wondering, aren't we doing cylindrical coordinates here, right? And how come I still x, y here? That's right, so we have to get rid of the x, y. So how do we get rid of x, y again? Exactly, right? So substitute the expression for r and y in terms of r and theta. Okay. Again, the simple trig identity, you have to apply it here in order to simplify it. So the first one gives you r squared, and the second one gives you 4 minus r squared. So now you have your z in terms of its own cylindrical coordinates, r and theta function. Okay, so once you find the z limits, the second step is to find r's limits, and third is the theta limits. Finding r and theta limits, it's exactly the same procedure when you're dealing with the polar coordinates. In terms of double integral, right? Polar coordinates. So starting from our origin, draw a reading line out of this shadow. First contact give you r mean, second contact give you the r max. So now you're dealing with the shadow now, right? To find r and theta. Okay. So basically this time we're scanning in the positive r-axis direction. So your r mean and here currently is 0 and R max always fall onto the edge of the circle, that's root 2, right? Root 2. Okay. So first contact, second contact. And last step, rotate this reading line starting from x-axis and rotate across the whole shadow. The whole shadow is the circle. So your theta mean and theta max is from 0 to 2 pi. Okay. So that's how you find the theta mean and theta max. So now you find the limits basically. Putting together, z goes from r squared to 4 minus r squared. Theta goes from 0 to root 2. R goes from 0 to root 2. Theta goes to 0 to 2 pi. So what are we integrating? This function says we're integrating x squared plus y squared dv, right? dv. So you cannot just leave the x squared plus y squared unattended. We have to replace this x and y with again with the r squared, r cosine theta and r sine theta. Okay. That's a replacement, substitution. And dv is changed to dz, rdr, and d theta. Right, that's the order. Okay. So this one here is due to the Jacobian calculation. You have r here, and don't forget the additional r. Okay, so the rest of the work, okay, this together here is another r squared. Okay, so there's a lot of r here. The rest of the work, I think it's not anything difficult at all. Okay, yeah, there's no tricky integrals in this particular. I want you to calculate, because I kind of did a different example from my lecture notes. So my notes doesn't have the r squared here. So with r squared, honestly, I don't know what the results is. So you try it out yourself. Say what the question here is. Okay, what the results is. Yeah, should be pretty straightforward. But the integral limits, right? As we just demonstrated it here, is that clear? Okay, yeah. Scanning through this whole thing to recreate this solid region D. So I want you to actually to think about this process again, right? So yeah, in terms of using cylindrical. First step, when you scan from in the positive z-axis here, it's like 3D printing. What did you print? You basically printed a small line segment set here, right? And second step, you're scanning in the r-axis direction. So basically, you're printing this line here starting from the z here, and then you're creating this half of circle kind of shape. And the last step is you go in the theta direction. So that half circle basically rotate 360 degrees. And now you covered every corner and you recreated this region D at here. Okay? Yeah. Yeah.
Look at the volume. Doesn't the R max change with the surface?
Does the R come again?
Does the R max change as you, because this R max is for the largest shadow, right? R is determined by the shadow, and the shadow is basically the whole edge, right, of the solid region D. Whatever the edge is, give you the shadow here. It doesn't mean that you still have to go back here. If I pick a small part of this region D, I have another shadow, right? But the shadow you draw here, keep in mind, it's basically the edge. It's like a 3D view. You know, you have a left view, a top view, right? Whatever the top view, in this case, top view, right? Whatever the top view is, that's the shadow. The R should depend on Z, R max.
No,
because we did the Z first, right? Second, when we do the R, we purely depends on this shadow now. So the shadow determines the R here, and shadow doesn't change anymore. However, if you change the order of integration, the things could be slightly different actually. Okay, so I'll show you an example next, and then actually I'll show you different orders. What would that matter? See? Okay, so let me give you an example right here. Okay. Very good thinking. This time, I'll deal with a cone. Okay, the region D is a cone right here. And you all love ice cream cone, but have you ever thought about the mathematical expression for a cone? Probably not. Right, that's a cone right here. For a cone, it's a surface. Okay, this is a cone. Okay, when you have a z equal to square root x squared plus y squared, that's a cone here. As a matter of fact, when you have a general expression like that, okay, that's a cone here. So the cone could be basically, you know, the edge of the cone, right, could be have a different angles, and that a value sort of determine the edge angle of the cone. Okay? Yeah. So I want you to remember this. Okay, so like you remember z equal to s squared plus y squared is a paraboloid, and you should remember as z equal to square root of x squared plus y squared will represent a cone now. So before we do an example at here, okay, let's think about this cone in here, because sometimes I deal with this shape quite a lot. So what's the cone equation, okay, in cylindrical coordinates? Because I write this cone equation in Cartesian coordinates, right? I can definitely express this cone or represent this cone using that 3 cylindrical coordinates there. So how do we do? It's very simple. We're going to replace the x and y with r cosine theta and r sine theta respectively. Your z will become, in this case here, your z will become what? R, right? Okay. Yeah, z becomes r. So when you see z equal to r, that's a cone. Okay. Yeah. Much simpler actually than the Cartesian coordinates equation. But what does z equal to r mean, right? Well, over here you get this z equal to r, and over here you get z equal to ar. Okay. So let's go back to this drawing in here. Let's think about back of what the z equal to r means at here. Okay. So let's say if I pick any point on the surface of the cone, okay, I'm picking point on the surface of the cone in here, and I can always draw an edge, right, from the origin connecting the point. So that's the edge line along the surface of the cone. If I look at this point I have picked and relates to the cylindrical coordinates, so this point has a z value, okay? And what about its cylindrical r coordinates? What do we do? Basically, here's your r here, right? Here's r. And I can create another one on the top here. So this is the z, also this is r on top. That makes sense, right? So now, when you have a cone like this, we're saying Z equal to R, basically. Okay? When you have a cone like this, we see Z equal to AR, right? So if you look at this geometry, so I want you basically always, this is something will help you in terms of finding limits if the region is a cone. I want you to focus on this triangle here. Okay, so this triangle. So this triangle here is a right triangle because R is perpendicular to the Z-axis. If I take it out, okay, over here, oh gosh, oh. If I take it out over here, and just look at this right triangle. Here's a Z, here is R, all right? Yeah. So I do have an angle at here, so let's call it phi angle. So this phi angle is what angle? Is the angle basically determining how wide the cone is, right? Yeah. So if you want to get more ice cream, you want to bring a cone with a bigger angle there, right? Yeah. Let's consider this case. If Z equal to R, what's phi here? If Z equal to R, 45 degrees. So technically, if I see Z equal to R, you say, okay, that's a cone. Alternatively, I can also tell you phi equal to 45 degrees. What is that? That's also a cone, right? As a matter of fact, the next in spherical coordinate, this is one of the spherical coordinates, essentially. Okay, yeah. So how about let's take a look at a different. Basically, I'll give you the a specific value here. So Z equal to 1 over root 3 square root x squared plus y squared. Okay? Yeah. What kind of cone is this one here? I can simplify this into 1 over root 3 times r. Okay? So basically I want you to kind of relate to the angle phi here. If this is a 1 over root 3 at here, other than 1, like here, then what will be the phi angle over here? Okay. So if this is Z here, I'm going to redraw the right triangle. Here's a Z, here's R. Now this time, what's the Z? Z equal to 1 over root 3 times R now, right? Okay. Here is still the angle phi. So using trig identity, tangential phi equal to the opposite side R divided by this side here. Okay. So it's the R over Z, which give me R divided by 1 root 3 R equal to root 3. So if you look at the table, when tangential phi equal to root 3, that's a special angle actually. How much? 60 degrees. That's right. Good. My drawing doesn't look like 60 degrees, but right? Yeah. So basically, when you have a cone like this, okay, 1 over root 3, something jumps to your mind is phi equal to 60 degrees, okay, for that cone. Is that good? Yeah. So we're trying to make all the formulas, not just dry formula, trying to make it something more concrete, right, popping into your mind. All right. Now, if I'm going to do some kind of a triple integral, okay, involving this cone in it here, I'll redraw the cone over here. Okay, let's say I have a cone given to you. Okay. And I want you to calculate, let's say you have a region D. Okay. You have a region D constitutes of this cone and plus a top plane, let's say Z equal to A. Okay. Or let's give a number here. Let's say x is Z equal to 4. So basically, this top surface here is Z equal to 4, right? Yeah. And then the rest of the region, the surface, is the cone. If this is the region D, and I want you to, can you find, let's say, the volume, right? Can you find the volume in here using cylindrical coordinates? Okay. So let's practice two different orders at here. Okay. Let's practice the two different, other than the traditional order. But let's try the traditional order here. If the first order is what is our typical dz, dr, d theta, right? Let's look at this order first. What will be the limits for dz, dr, d theta? Okay, so this is what I call order number 1. If this is the order we're going to choose, right, as we always do, the next step is to sketch the shadow, right? Yeah. So you have a shadow over here. Okay. Like that. Good. So this shadow is basically a circle. If you project that, that's the circle on the top of the cone right here. What's the circle equation then? Equal to 2? Equal to 4, right? Actually, well, this circle is basically, when you equate these two equations, you get x squared plus y squared equal to 4 squared. Is that okay? Yeah. So this circle has a radius of 4 at here. Okay. That's your shadow. Once you get a shadow, pick points in the shadow, go along the positive z-axis direction. You will have a first contact, second contact. First contact falls onto the surface of the cone. Second contact falls on the top surface. So you will have your z-mean is the cone surface to the top one, that's 4, right? Okay. So what should I put as the lower limit? Sorry, come again? R, that's right. Okay. Because your first contact falls onto this cone surface. And the cone surface, in terms of cylindrical coordinates, is z equal to r. So here is r right here. And then look for r limits and theta limits. So this step, scanning in the r direction, 0 to 4. Last step, theta, 0 to 2 pi. So dz is the first integral, and then rdr and d theta, okay, are the next two orders. That's how you find the limits. Okay? Yeah. So what if I use a different order at here? Let's see if I try this order. dr, dz, d theta. and what will be the limits for this at here. So the tricky part is if I follow my previous step, if I choose dr d theta, dz d theta, then I'm supposed to sketch a shadow for dz d theta, isn't it, right? But it's very hard to actually visualize that in the x, y, z coordinates. Okay, so here instead of draw the shadow, let's rely on the idea of scanning. Okay, scanning through this region D in the order of r theta z, and whenever you do the scanning, you always scan in that direction of the axis. First step, you scan in the r direction. Okay, the first step scan is sort of a general scan. Let me redraw it here. So general scan, let's see, I'm going to pick a point anywhere, along the z-axis direction. General. So now I'm going to scan through in the r-axis direction. So starting from here, okay, scan through in the r-axis direction. R-axis direction is basically you draw a reading line out of it. Which direction you draw doesn't matter, right? So you draw a reading line out of that point, but in the r-axis direction. So you basically, like here, you draw one here, right? But now this time you draw it anywhere here. So you scan this direction or that direction, doesn't matter. So the first step, scan, is basically you created a small segment of line at here. But you can literally see your first contact, right? Because you scan, because it basically falls onto the contact here. So your r min is 0, and your r max falls onto the surface of the cone. And r max, surface of the cone is z equal to r. So this time r max must be z. Okay? That's the first step of scan. Your 3D printing, you printed a small segment set here. Second step, you're going to print in the direction of z now. So basically you're going to print in the z direction. This is your z direction. So this line here, you're going to basically print up to here. That makes sense? So you're scanning in the z direction. Starting from here and ending here. So your z min must be 0 and your z max must be 4. And the last step, you're going to print in the r-axis direction. So basically rotate this half triangle here 360 degrees. Theta min is 0 and theta max is 2 pi. So you create an object covering all the edges, all the corners of region D. That make sense? Yeah. So this idea of scanning, right, is sometimes better than anything else. So I want you to think about, what about d theta, dr, dz? Okay, another order. Then what will be the limits for theta, r, and z? Okay. This one is a little bit trickier. Okay, so I'm kind of running out of time here, and I'll leave it as a question mark. Okay, if you're interested, try it out yourself. Any questions? All good? Okay, thank you.